Nellie Newton whirls an empty tin can attached to the end of a string in a horizontal circular path. The pull she exerts on the string keeps the can circling. Any force directed to a fixed center is called a centripetal force. Centripetal means center-seeking or toward the center. Earth's gravitational pull on the moon is a centripetal force, as is the electric force that pulls electrons in circular paths about atomic nuclei. Centripetal force takes many forms. Centripetal force on Nellie's whirling can depends upon the mass of the can m, the can speed, and the radius of curvature r, which in this case is the length of the string. In lab, you'll likely use the exact relationship. F equals mv squared over r, where force is measured in newtons, mass in kilograms, speed in meters per second, and radial distance in meters. Note that speed is squared, so twice the speed needs 4 times the force. This equation is simply the familiar form of Newton's second law when expressed as F equals ma, where here centripetal acceleration is v squared over r, and to keep this lesson brief, I won't go into how acceleration a becomes v squared over r for circular motion, perhaps for further study. We already know objects in circular motion accelerate because the velocity changes in direction. So now we see that the force producing circular motion is F equals mv squared over r. To a close approximation, we can say the centripetal force on Nellie's can is tension T in the string. It would be exactly T if the string maintained a horizontal position throughout the swing. More about this in a bit. Here's a top view of the whirling can. Do you see the force on the can directed inward or outward? I hope at this point you don't think, as many people think, that it's outward. Centripetal force acts inward toward the center of circular motion. Suppose the string breaks. In what direction will the can travel? Will it travel outward like this? No way! With no force holding it in a circle, in accord with Newton's first law, it will move in a straight line that is tangent to its path at the moment the string breaks. In fact, we say the velocity of the can moving in a circle is tangential velocity, velocity that is tangential to the path. Consider an automobile driving on a muddy road. If adhesion of mud on each of its spinning tires is not great enough to hold mud on the tires, that is, if centripetal force is insufficient, mud flies off. In what direction? I hope you didn't say radially outward, as many people think. The mud flies off in straight line tangents to the tire surface. The green arrows show the tangential directions. Here's a top view of a car rounding a curve. The path is part of a circle, so there's got to be a centripetal force on the car. What kind of force comprises the centripetal force? Can you see its friction between the road and the tires? I hope you agree. We ask how much friction? We then apply the equation for centripetal force. Here, italic F stands for friction, m is the mass of the car, v is its speed, and r is the radial distance, the distance to the center of curvature of the road. If friction is too weak, then the car will skid from the curve. Here's an interesting question. Can a car be driven along a curved road if there is no friction between its tires and the road surface? The answer is a delightful yes, if the road is properly banked. Let's look at the principal forces acting on the car when there is no friction. That's its weight, mg, and the normal force, n. Recall that the normal force is always at right angles to the supporting surface. We indicate the radial distance with a green line. Now here's the interesting part. There isn't a force acting directly toward the center of curvature of the road. So maybe there's no centripetal force? But consider vector n. Aha! Vector n has a vector component along the horizontal and toward the center of curvature. It is this component of n that we call n sub x that produces the centripetal force to keep the car on its curved path. When n sub x satisfies the equation mv squared over r, no friction force is needed, none. The car would make the turn even if the road surface were slippery ice. And what's n sub y? Since there's no vertical acceleration, the magnitude of n sub y equals mg. Yum! Want to reduce tire wear when driving? Then drive on curved roads that are banked. Often you'll notice proper speeds posted for banked roadways. These speeds are calculated by engineers who work the angle of bank into the centripetal force equation. In the calculations, mass m cancels, so when you drive at the posted speed, whatever the mass of your car, you'll sail around the curve as if friction didn't exist. Next time you're riding on a banked road, think physics. Let's return to where we began, to Nellie. We said the tension T in her string was approximately equal to the centripetal force needed to keep the can moving in a circle. Why approximately? Because the string really isn't horizontal. Even for higher speeds, she can impart to the can. Note that vector T points a bit above the horizontal. So the needed centripetal force is the horizontal component of T that we call T sub x, which does lie along the radial direction. We can go further. How about the vertical direction? Since there's no vertical changes in motion, there has to be an equal and opposite force to counteract downward mg. That comes from the vertical component of T, T sub y. Is this yum or what? So the two vector components of T are quite intriguing. As said, the horizontal component supplies the needed centripetal force, and the vertical component equals the magnitude of mg. This is particularly important when the tension vector is even farther from the horizontal, like in this conical pendulum. That's yum too. I want to leave you with a question. If Nellie shortened her string to half its length, but kept the same speed v for the whirling can, how would the tension in the string be affected? Until next time, good energy.